So let's continue with this idea. If you have forces acting on curved surfaces, all right. So let's just take a. Okay, so let's just take something like this. So if this is an object, and then you have a curved surface, and then it goes all the way up till here. Again, this is a straight line. So this thing is completely filled with some liquid. So what I'm going to do now, I will just separate this curved surface out from here. So if this is the curved surface, and in fact I'm just more concerned with the fluid in there. So this will be the fluid. Okay, and then you have some force acting on top of this. Okay, so the idea is there is some fluid on top of this. Alright, so I mean there is the fluid, and that it has some weight, so that weight is actually acting somewhere over here. So around, so half of this line, so that's where the weight of this fluid will be acting, and I can, which is simply rho g h times the area. So that will be the weight of the fluid that is sitting on top of it, and then at the same time this fluid has its own weight, so that will be acting at the centroid. So if this is the centroid of this the shape, the weight of this will be acting somewhere over here. So you have W1 and then you have W2, which is the weight of this one, and at the same time you have as you will notice that you have so much fluid on the top. I mean, so this is the weight where it's acting, then you have the fluid weight, but at the same time you have this hydrostatic forces which being developed over here. So now you have this pressure or this force acting in this direction, so which I am representing by F of H. So this is the horizontal force, so F of H will be acting in this direction. So we do know this F of H is acting in this direction. We don't know the location of that force. And how do you actually so first of all, what that force would be, so the horizontal force is equals to gamma hc times A. So again, it will be height hc, okay, and so this height hc times the area times the gamma. And just to mention that this hc, if you look at this object over here, I mean this fluid, so let me in fact draw the same thing over here now. This has some width. Okay, so anytime you have an object, it will have some width. Okay, and this is not the best of the pictures, but the idea is, if you think about this element over here, so this fluid actually, once you think about it, this has some width, and this shape is a rectangular shape, and we are looking at the centroid of this shape. So that's the distance from the centroid to the top of the fluid layer. So this is where the fluid is starting. So this distance is our HC. So that is the distance you need to put in here to find your horizontal force. All right, so this is what you will be using, and in a similar way, when you are computing for your resultant force where that force is acting, so in that case you will have to use F of H times Y of R, or like where this resultant force is acting, is equals to, in this case it should be equals to, I mean you can write it as PdA times y, and then y is equals to y rho g So y rho g v, okay, so that's another y here, and then you have d. Okay, so this implies that rho g y square dA is equals to fh yr, and this is the second moment of area. So in a similar way, what we have done before, what I have showed you guys before, you can find the resultant force is equals to Ixxc plus yca plus yc. So that will tell you where that horizontal force acting on this object. Okay, so that's where this force is acting with respect to some place on the top. So that's where the horizontal force would be acting. The vertical forces, one is halfway in middle, so whatever, if this is your L, so this distance will be L over 2, and that is the centroid. Okay, and then this is also the weight of the fluid, which is simply gamma times V, and then you have some weight of the fluid from the top also. Okay, so the total force, so F total, because you have a horizontal force and you have two vertical forces, one here, one here, so the total force would actually be FH square plus FV square. So that will give you the total force, the magnitude of the total force, and where that force will be acting, it will be tangent inverse times FV over FH. So you have a horizontal force acting this way, you have some vertical forces acting this way, so the resultant will be, it might or might not, but it will pass somewhere over here. So this will be given by this angle theta. So you can basically compute that theta and you have the magnitude for the total force. Alright, so let's take a look at a quick example for this one, for a curved surface. Okay, so the example is a quarter circle gate is hinged at C. Find horizontal force P required to hold the gate stationary. The width of the gate is 3 meters. So as you will notice, this thing is completely filled with the fluid, with water. In fact, I should say water. And this is where the hinge is, C. And if there's no force being applied, this water will actually, it will lower this gate down and it will flow this way. So we have to apply some force so that we can counter the force that's being exerted by this water. Okay, so I'm gonna, again, there is no force from the top. The atmospheric pressure will be balanced on this side, but if you have some weight on the top, you have to include that. But in this case, there is no water above it, so we will only have to worry about the water of this section. Okay, so I'm going to take this thing out. So in fact, let me draw it here. So this is the section, and this has a width of 3. Okay, so I'm going to define this as something like that. So okay, so that's what the fluid looks like, and this is the cross-sectional area that I am concerned with, because as I mentioned, the horizontal force requires this distance from the top to the centroid. So the centroid, if I look at from this side, this shape will have a width of 3. So the width is 3. And then the height of this is 2. So somewhere in the middle, we will have this y of c, which actually is, so half of it, so y of c is 1. So if I am looking at the horizontal force, so the horizontal force is simply gamma at c times a, so which is actually equals to, so gamma in this case, I am taking that to be 9790 Newton per meter cube, times 1 meter, which is hc, times the 6 meter square, which is the cross-sectional area of that fluid element. And I mean, the way we are deriving this, you can look at the derivation from today's the video or the last video that I talked about for a vertical, the forces on the vertical plate. Okay, so when I multiply all of these together, it gives me 58740 newtons. So this is the force that's being applied in this direction. We don't know the location of that force yet, but we do know the magnitude of that. The way we can find the where this force is acting, I will use this relationship y of r, which is Ixc over yca plus yc, and we have this yc, which is 1. So yc, the area is 3 times 2. The only missing quantity is this Ixc, so that I can find out by, so which is 1 over 12 b cube times 2 to the power third. And when so this is the second moment of area for a shape that looks something like this. So when I put all of these things together, so it gives me 4 by 12 plus 1, so which is 1 by 3 plus 1, and all of this is 4 by 3, which is 1.33 meters. So the force will be acting, so again if I take it out like this, so force will be acting, and this is 2 meters, so force will be acting at a distance of 1.33 meters from the top. Okay, so that's what this quantity represents, 1.33 meters from the top. So that's where the horizontal force is acting. Okay, so this is for the horizontal force, and now we also have a vertical force which is acting in this direction. So first of all, we have to find out what that vertical force would be. So to calculate that vertical force, which is simply the weight of the water, is gamma times the volume. So gamma in this case is 9790 Newton per meter cube, and the volume of this is because it's a quarter of if I think about it, is the cross-sectional area times the length, which gives me the volume. This is a cylinder, so I can find out pi r square, which is like the radius is this r, and then this is your length, or the width in this case, so pi r square L, and I have to divide this by 4 because we only have like the fourth of that. So that's why I have to divide it by 4. So that will in fact be 1 over 4 pi r square, where r is actually in this case r is 2 square times 3, where 3 is the width. So when I multiply all of this, it gives me a weight of 92280 newtons. So once I have this weight, and this weight is acting at the centroid of this of the fluid. Okay, centroid of the fluid geometry, I should say. Okay, so if I look at this, the geometry looks something like this. Alright, so that's what our geometry is. And the centroid is this point here, and the distance from here to here is 4 r by 3 pi. Okay, so that's this distance. So I can compute that, and in fact this comes out to be 0.848 meters. So I do know where this weight force is acting, and we also have where this horizontal force is acting. So we can take the moment, about C, which is this point over here. So this is our hinge. So we're going to take the moment about the C, and we have to find what this force P would be, the required force P. So the clockwise I will take as negative moments, and the counterclockwise I will take the positive. So the first one is a negative because it's trying to rotate it clockwise, so it's going to be minus P times the distance, which actually in this case is 2 meters. And the next force is, which is this, it's trying to rotate it counterclockwise, so it is 92280 times 0.848 meters. And then this force, this is also trying to rotate counterclockwise, so plus 58740, and this is acting at 2/3, and that is equals to 0. So if you are taking about the moments, and if you want to balance this out, so the summation of all the moments have to be equal to 0. So 2p is equals to 31960 plus 78253, and then p is simply 58.7 kilonewtons. So this much of a force you need to apply to keep this thing, so that the water does not move this plate and flow over. So that's the amount of force you would need to apply. Alright, so that's pretty much what I wanted to cover for hydrostatic forces, and in the next video I will talk about the buoyancy, and then we will look at the stability. See you guys.